Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list published on September 3rd, 2025, about 4 days ago. The standout idea is a graph-based pipeline for offline reinforcement learning in sepsis care, where a GraphSAGE encoder ultimately delivers the best downstream policy value with weighted importance sampling around 0.75, despite slower training. The paper is titled Exploring a Graph-Based Approach to Offline Reinforcement Learning for Sepsis Treatment, and the implications for model training are quite significant. In short, dynamic heterogeneous graphs beat a plain autoencoder in final policy quality, while a GATv2 encoder reconstructs better but harms policy learning and adds heavy compute. On X, reactions focus on method over message. Commenters praise the clean separation between representation learning and policy learning. Note GraphSAGE's stronger policy value despite slower training, and caution that better reconstruction can mislead downstream rewards. Engagement appears modest. Alright, the previous segment introduced typed attributed graphs and message passing. Figure 1 presents the full pipeline that ties those ideas to offline reinforcement learning. Data flow moves from the data provider to an encoder, whose latent representations feed both a decoder for next observation prediction and the dBCQ policy for control. The right branch shows two encoder paths, an autoencoder flow and a GNN flow, where graph modeling and the GNN encoder are highlighted because they are the main contribution. The shared latent space anchors both representation learning and policy learning. So the previous figure laid out the pipeline. Figure 2 shows the type graph that defines each trajectory as a dynamic heterogeneous graph, which standardizes nodes and edges for encoding. A single patient node carries time-invariant attributes like gender and age, while many time-step nodes hold vitals that change over time. Directed edges between successive time steps store the action taken, and a terminal node links to the final time step to mark episode end. Bidirectional patient-to-time step edges enable message passing in both directions. Alright, the previous figure established the type schema. Figure 3 shows one concrete patient trajectory with 7 time steps, which clarifies how edges encode both relationships and actions. The central patient node connects bidirectionally to every time step node, labeled T1 through T7, so message passing aggregates history via has edges. Directed links labeled action chain the time steps in order, and the last time step points to a terminal node that marks episode end and reward. This layout matches the snapshot construction used for the encoder, while the previous figure illustrated one patient trajectory. Figure 4 shows policy value over 1 million training steps, measured by weighted importance sampling, which estimates how good a learned policy is using log data. The green autoencoder curve climbs quickly to about 0.68 and then plateaus, so it learns fast but stops improving. The dark blue GraphSAGE curve rises slowly, then after roughly 375,000 steps, it accelerates and reaches around 0.75. The light blue GATv2 curve lags, showing noticeable gains only after 600,000 steps and ending just above 0.5. Okay, the previous figure compared validation losses. Table 2 lists the hyperparameter choices explored for the GraphSAGE encoder, which clarifies how depth and width were tuned. The runs vary the output feature size, noted as fout, between 64 and 128, and the number of convolution layers, noted as encond, between 2 and 3. The highlighted Misty Mountain 42 setting, with fout 64 and encond 2, corresponds to the best validation loss because larger width tended to overfit, while extra depth slightly hurt generalization. Wrapping up, 2 takeaways stand out. Graph-structured patient trajectories enable stronger offline reinforcement learning, with GraphSAGE delivering the best final policy value, and better reconstruction does not guarantee better control, as GATv2 shows. The broader implication is clear. Clinical decision models must prioritize control-oriented representations over prettiest reconstructions. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.